Our next presentation is on space lock puzzles and verifiable space-hard functions from root finding in sparse polynomials by Nico Döttling, Jesko Jumovic, and Antoine Jou. And Jesko is giving the talk.
Yes. Hello, I'm Jesko Jumovic, and this is joint work with my advisor Nico Döttling and Antoine Jou. And I'll be talking about space log puzzles and verifiable space-hard functions from root finding in sparse polynomials. At the end of the talk, I hope you will know what all of that means. Okay. So our story today starts with verifiable delay functions, both the concept and the paper. So in 2018, the ePrint version is 2019, but anyway, in 2018, there was this paper, verifiable delay functions, and they defined a notion, verifiable delay function. F of x is a verifiable delay function if it takes a long time to compute it. It produces a proof, and it's fast to verify the proof. And the proof verifies that the output of the function is actually that y is the output of the function. And we kind of need standard soundness and completeness, but this is really not the point, so I'll not define anything. Okay, maybe more pictorially, here on the left side, there's some random x. You evaluate f with some time parameter t on x. After a time t, you get an output y and a proof. And kind of even if you have more parallel computation, it doesn't really help you to compute the function faster. So that's the delay part of this. Okay. Other than this definition, the authors of the VDF paper, Bonnet et al., they also introduced a candidate. And the candidate is based on polynomials over finite fields. So here we have h of x, which is a polynomial of a finite field. We require it to be a permutation, high degree, so the time parameter is scales with the degree, and it needs to be fast to evaluate it. And now they conjecture that inverting this polynomial is a weak VDF. Okay. Why is it a VDF, not just a delay function? Because checking that h inverse of x is y is fairly easy, because you can just evaluate h on y, and because one of the conditions is that it's fast to evaluate, this is enough. And because it's a polynomial, because it's a permutation, this is unique. Okay, and they justify this assumption by the computation being seems to be inherently sequential, and up to a certain degree, that's why there's a weak. And now I'll get to the negatives of this construction, so the problems. First of all, if you have a lot of parallel processes, I don't really need to get into the exact numbers, then this becomes very fast, because essentially you can just do parallel linear algebra to solve these equations. So this is already not that great, but also these permutation polynomials that also are fast to evaluate and have high degree are hard to find if you want them to be non-trivial. And so they are so hard to find that in the literature they're even called exceptional polynomials. And here's the polynomial that Bonnet et al. Conjecture in their paper, and as far as we could determine at the time of the publication of this VDF paper, this was the only known non-trivial exceptional polynomial known to people. Okay, so our first contribution is that we actually break the sequentiality of this, of inverting this function, and I'll give you a sketch of this break. Okay, here's the function again at the top. Oh, and okay, these polynomials are called Guralnik-Müller polynomials because those are the people that introduced this polynomial. Okay, finding a solution for h of x being y is the same as computing a root of h of x minus y. Okay, that's easy enough. Then from this paper, Guralnik-Müller, they give us the statement that if theta is the q minus first root of unity in the algebraic closure, then we get this nice term here. And if you notice on the right side, there's only terms that are where x is to the power of something with q, or x to the 1. Now, if we want a solution such that h of x is y, then we get that for I being 0, this thing here is 0, and therefore the entire product here is 0, and therefore the entire right side is 0. And this is exactly what we want. So now we have that for any solution that we want, this right side is 0. Now, because these are because taking x to the q is a FP homomorphism, that q is p to the something. I think you called it m on the previous slide. So taking x to the power of p is a FP homomorphism, and therefore this is a linear function over FP, and so you can just solve it with linear algebra. Okay, so this is the break. If I lost you, come back now. Now it's all cryptographic, normal algebra. Okay, now back to our problems. How do we solve the problems? First of all, the problem, if there's too many parallel processes, then linear algebra becomes fast. How do we solve this? We just don't assume time like a sequential hardness. We just assume space hardness. So we hope that it takes a lot of space to solve these equations, and kind of all known algorithms kind of need that, except for the one that we just showed. But I'll get to why that won't help for what we do. And then what do we get if we just assume space hardness? So we have some random x. We evaluate the function f for some space parameter x, s and on x. Now we have a big error. So you need a lot of space to compute it, but we don't require anything on the how long it takes. And this even is the case if you have more parallel computation that might even run longer, but essentially, as long as you don't use as much space as S, you will not be able to compute the function. And also you get an output Y and a proof. Okay, the same. So, but you've noticed that we switched from time hardness to space hardness. Okay, now if we use the same polynomials as before, our algorithm that I just showed you in the previous slide would also break this, because our algorithm also doesn't use a lot of space. But so our solution is just use less structured polynomials. Namely, we drop the permutation requirement. And these are much easier to build. Oh, okay, I'll get to that. These are much easier to build. You just pick a random sparse polynomial of the degree that you want. Okay. Okay, is space hardness reasonable? Any algorithm that we found is just brute force trying, or it uses the polynomial in a way that it treats it as if it was dense, and if it does that, then essentially to represent the polynomial, you need the space to grow in the degree. Okay, that's what I said. Okay, now how do you build these? Okay, I mean, the idea is the same, but now we have the problem that our H no longer is a permutation. So we have the problem that for some Y, there's no input that would map to it, and also that there are different inputs that map to the same value. So now we actually need to prove that we've done the inverting the polynomial, otherwise you will not get uniqueness for this. Okay. So general purpose snarks are enough to do this. We built a tailor-made snark that kind of uses something approximating polynomial commitments that uses the structure of inverting this polynomial. I will not get into the details of this too much. Okay, now to our other applications, which also starts with time. And this is a work from Rivers, Jamir, and Wagner. It's about time lock puzzles. So here, it kind of looks like encryption. You generate a puzzle Z with a time parameter T. And now you give this puzzle to a solver, and the solver needs T time to open this puzzle and doesn't require any secret key or anything. And after the time, it's supposed to open to M. M is the message that we generated the puzzle with. And now, even if you have more parallel computation, you will not get this M faster. This is what the time lock puzzles give you. And again, because now we don't require time hardness, we require space hardness. We define it a similar way. You generate a puzzle Z with a space parameter S and a message M. You give this to a solver. The solver needs a lot of space to open this and gets out the message M. If they have little storage but long running time, they will not be able to open it any faster. This construction is a bit simpler to look at, so that's why I go into the details here. So how does our gen look like? I sample a sparse polynomial with where the constant coefficient is random, and the degree of the polynomial will be the space hardness of this function. Now I output this polynomial h of x minus m, and now the solver does the following: just interprets it as a polynomial and computes the root of it. Oh, now we have a problem. We don't have the guarantee that g of x is a permutation polynomial, so technically this could output multiple values. So we need to introduce a new mechanism. I mean, this would work if g of x was a permutation polynomial, because then there would only be one possible message here, because g of x would only have one root. But so we need to add a mechanism to determine this. So I will modify this construction slightly. Again, I sample a sparse polynomial with a constant, random constant coefficient, sample a key k, and now the idea really is that we encrypt our message with respect to this key, and we have this padding to make sure that that we can kind of check the validity of the key k. So now I do the same thing. I put the key k as the I subtract the key k from this polynomial, and I also output the ciphertext. Now when I solve this thing, I get n keys k, and I just go through all the keys and check which of them decrypts to something that ends in the padding, and because there's like not that many k's, you can check this, and this validity check is only achieved if use the correct key, and then M will actually be the message that you input here. Okay, yes, so this is already it. So now I hope you know what spacelog puzzles are, what verifiable space-hard functions are, and root finding in sparse polynomials. So I think I've achieved the, okay, thank you.
Okay, thanks for talk. We really don't have time for questions because we're over time, so.
Oh, sorry.